Good afternoon, everyone. This is Mike Montefusco, National Weather Service, Wakefield, Virginia. This is our basic SKYWARN spotter training presentation for 2025. We'll go into the topics here in just a moment, but we have the basic weather information you need to know with this class to give you the ability to keep yourself and your family safe during times of severe weather. We'll be talking about some of the following topics here with our class. We'll be talking about the role of the spotter, getting into the risk of storms and the hazards that they present, going into watches versus warnings and advisories, and how we keep you safe from the National Weather Service perspective. Next, we'll be going into some thunderstorm meteorology, talking about the types of severe weather, thunderstorm formation, straight line winds, hail, flash flooding, wall clouds, funnel clouds, tornadoes. Those are some of the terms that we'll be talking about as we go through those topics. We'll be getting into reporting procedures, how you get a hold of us during severe weather and after severe weather moves through your area. And lastly, we'll have some spotter safety notes to help keep you safe during severe weather as well. So let's go ahead and get started and talk about the role of a spotter. Our National Weather Service spotters are volunteers who fundamentally report real-time severe weather to us in the National Weather Service. And that information that we receive from our spotters is really, really important because it allows us to issue more accurate and more timely warnings. We have a lot of ways to get information out here from a National Weather Service perspective, and we can let folks know what's actually going on in real time. And that's really great. But in terms of what is actually happening, what's actually happening where our spotters live, that's really critical information that we really thrive on and really need to get those warnings out in a more timely way. So spotters really can and do help us keep our community safe during severe weather, and we very much appreciate all that our spotters do for us. In terms of what our spotters see out in real time, it's more like what you would see there on the right. Now, hopefully it's not a tornado moving through the middle of your town. We certainly don't want that. But what it's actually getting at is what's happening in your town, what's happening as those storms move through is what you're experiencing. We can, as you can see on the image on the left, have a pretty good indication of the weather that's moving through your area. So we can look at that radar image right there. We can what that's called is a hook echo. That's a pretty good indication that we have at least a rotating thunderstorm that's producing a thunderstorm that could be tornadic. The only way for us to have that information for certain, that ground truth information, the only way we can have that information is for our spotters to get a hold of us and let us know what it is that they're seeing in real time. And that real-time verification adds credibility, enhances public response, and improves warning accuracy. If I told you the next town over from you experienced a thunderstorm, and in that thunderstorm they had quarter-size hail or larger, that's something that you would say, okay, maybe I need to get to a place of safety. Or maybe the next town next over to you received 60-mile-per-hour winds and knocked some trees down, or a thunderstorm that was producing a tornado. You said, hey, maybe I need to get to a place of safety. Maybe we need to get undercover to make sure that, we're in a good place for when this storm moves through. So that's exactly what we're talking about in terms of that real-time verification adding credibility. We can certainly have a good idea what our storms are presenting out in the community, those dangers that they're producing, but having that little bit of extra ground truth is really, really important to let folks know that, hey, you really need to get to safety here because this is a potentially serious situation. Now, in terms of our radar, what you're seeing on the radar underneath that dome at our office here in Wakefield is what it's always doing, which is in rotation mode. It's always in surveillance, putting sound pulses out and listening for our storms to move through. And what those sound pulses are doing is they're going out and they are in surveillance mode looking for raindrops or items out there to hit. And as that sound pulse goes out and it hits our raindrops, the raindrops are going to, in turn, send that signal back to the radar, reflect it back to the radar. So that is the reflectivity product. If you've got a radar application on your phone, or if you're watching the television news in the evening, or if you're watching radar on your computer, that you're typically looking at the reflectivity product, and that's going to tell you how much of that signal from our radar is being reflected back. Generally, the hotter colors, the reds, the yellows, the oranges, that's going to tell you you have a large amount of reflectivity. So lots of rainfall, or lots of hail, or lots of something is being reflected back in the cloud by that phenomena that's in the cloud. So that's the reflectivity piece. The velocity is the direction in which the air is moving, and that is where we would see a lot of the terms about Doppler radar. You hear about Doppler radar all the time. That'd be, Doppler 6, Doppler 12, Doppler 19, whatever it happens to be in your area. That velocity is the radar's reflection of how that air is moving. Is it moving towards the area? Is it moving away from the area? The best way to relate that is if you're driving down the road and you hear a emergency siren from a police vehicle or a fire engine or whatever it is, that sound is going to sound differently in front of you than it's going to sound behind you. If you hear a train coming, that train horn is going to sound differently in front of you than it's going to sound behind you, and it'll make that different sound as the vehicle or as the train passes you. That is the Doppler effect in action. That is the sound moving towards you versus the sound moving away from you. And most importantly, the radar has the ability to determine whether that is happening and what's going on. So that's very important, because if we have thunderstorm circulation coming out of our thunderstorms, it's going to be able to determine which way that wind is moving. Now, there is, importantly, some significant limitations with the radar that need to be kept in mind. Now, number one, because of the curvature of the Earth, the farther away our radar gets from the emanation point. So the farther away, in our case, the radar gets away from Wakefield. Number one, the higher that beam gets, the higher end that beam gets above the ground level. And number two, the wider that beam gets. You can see it's really, really fine in the or close together here in the right close to the radar. You get far away, the beam widens, and we start to lose resolution. So that's going to do a couple of things. Number one, we can get a really good picture. Figure 50, 70, 90 miles away from the radar, we can get a pretty good shot of what is actually happening in our radar. So we can get a pretty good idea of what's happening throughout a thunderstorm as it's moving through. When you get to location B, our radar can sample up to 200, 250 miles, even greater miles away from us here in our office in Wakefield, or any weather service forecast office. But the farther and farther away you go, the worse the resolution is going to be. So the worse that picture that we're going to get of the thunderstorm is going to be. It's going to be more of a couple of puzzle pieces and a blurry object versus a very, very tight looking thunderstorm that we can get a real good idea of what's happening. So the farther away we go, the less we know about what it is that we're seeing. So the way we can remedy that is, number one, we have other weather service radars that we can use to supplement that data. But also, most importantly, is our spotters help us to figure out what's happening in between the cracks and crevices in between our service areas, and where some of the data area is a little bit weak. We use our spotters and our reports that we receive to kind of fill in those blanks that we might not necessarily have all the information for. Point being, our spotters help us to save lives, and we very much appreciate all that our spotters do to help us do that. So getting into the risk for our thunderstorms, this is one of our handout documents. If you haven't already received this, you'll get this upon completion of the course. You'll have this emailed to you. But generally ahead of time, a day or two ahead of time, you'll typically get briefing type packages from us. You might see something from our social media feeds, for example. You might see something from our friends in the media kind of talking about our outlook, the storms that we're expecting for the day. We'll do that through our Storm Prediction Center outlooks from the national level. Perhaps the hazardous weather outlooks, we'll talk about that in a little bit. But that's generally kind of a heads up type of product, let you know what we're expecting and when we're expecting it. As we get closer, we'll start talking about watches. So thunderstorm watches, tornado watches, flood watches, monitoring conditions, checking the latest forecast. That's how you get that information. We say to stay weather aware for that reason, because those storms, as they move through, they could present that threat for strong to severe storms later on in the day. So that is the watch phase. When we get into the warning phase, that is something where we say this is about to happen or it's happening now. So strong thunderstorms, tornadoes, floods, that's telling you to take shelter, to get to a place of safety, because that's happening now. And really, when we get into this type of situation where those storms are moving through, we only have a very small amount of time to make a difference. So we tell folks to get to a place of safety and make sure that you're able to ride out the storm safely. And we'll give you some tips at the end for how you can do that. But that's generally our ready, set, go continuum from outlook to warning. That's how we would handle things here from a National Weather Service perspective. So this is the way that the Storm Prediction Center will message the thunderstorms outlook as we move through. Number one, the generally a week to 7 days or 8 days out ahead of our storms. We'll kind of handle it with this type of setup, where we'll go from ascending scale from 1 to 5, from more isolated threat to a more widespread threat. And the higher this number goes from 1 to 5, the more widespread and the stronger and more intense we expect our storms to be. So typically the lower end of things, where what we call general thunderstorms, we don't really expect strong to severe storms. But again, the thunderstorms don't really think about what we're rating them, right? So you can have a general thunderstorm outlook and still have a strong storm or two. So you can have lightning, you can have flooding that can occur within all thunderstorms. But typically in terms of aerial coverage of storms, we'll go from 1 to 2 to 3, 4, 5 with respect to how our expectation is of how that event is going to go. In terms of planning things out, a few days ahead of time, we try to make sure that our friends out there have enough information to make these decisions for themselves in terms of making sure you have emergency supplies, knowing where the safe places are, where you are, having a communication plan with your friends or family or coworkers in terms of where to go in place of severe weather, how to keep yourself safe, things of that nature. The day before, you might want to adjust your plans for severe weather. Like if we're expecting storms in the afternoon, maybe you do things a little bit earlier in the day, or maybe you postpone it for another day. Make sure your phone has the ability to receive WEAs. We'll talk about WEAs here as we go forward, but those WEAs are alerts that come to your phone, that you have those heads ups to let you know this is what's occurring, and we'll let you know what's moving your way. Lastly, you might want to ensure that your severe weather shelter is clean and accessible. You don't have clutter in the way. You don't have things that are blocking your path or ways to get to safety. That's a very important thing there. And then the day of, again, kind of review your communication plan. Know what you're going to do, where you're going to go. And when a warning is issued, go ahead and execute your plan. You might have only a short amount of time to get that plan executed. So just go ahead and do that. We did get a question here. Can you explain the difference between a watch versus warning? And we certainly can. We'll do that in a couple of slides here. And you'll see the difference there. And that's basically getting into ingredients. So we're watching ingredients for storms coming together. And by the time we get into the warning phase, those ingredients have come together. So we'll talk about that as we go forward here. Now, in terms of hazardous product definitions, in terms of what we're actually messaging to our users with what's coming, our briefing page is a good way to do that. So this is our webpage at weather.gov/Wakefield. First, I'll call your attention to the Weather Service weather radio, NOAA Weather Radio. It's that weather radio icon in the pink there on the bottom, and you'll get immediate broadcast of watches and warnings. We call that the smoke alarm for weather for a reason, because it's thinking about the weather even if you're not. So really, definitely recommend having a weather radio at your disposal. If you don't have one, definitely recommend picking one up if you can, if resources allow. Pretty much every place has them at this point. You can pick them up in grocery stores, electronic stores, available pretty much everywhere online now. So it's just simply making sure that you have the ability to get those weather alerts as they come in. Secondly, the SKYWARN page, which is kind of in that circle or that squared icon there. You can just click on that SKYWARN page and you'll have all the resources for this course. So everything that we're handing out here that you'll receive via your spotter packet, you'll receive that, or you'll have access to that there. And access to this class recorded is going to be there. All of our handouts will be available here. Future classes, all of that information will be there, and you also will have the ability to send automated reports through there, which is another good thing that we would have available for you. The only thing I would ask in exchange is if you have something that's time sensitive, like if you're watching a tornado moving through where your location is, go ahead and report that via phone. Call us and let us know, because that could be time sensitive information that we need to know, really, really quickly. So go ahead and drop us a line via phone if at all possible. We'll have our information available at the end here for your information on that. The briefings is that section is available to help you kind of self-brief, let you know what's going on from a weather perspective at all times. So you'll be able to click this link there and get a good information in terms of what's happening, what we're expecting, access to model data and the latest observations and the latest forecast products. All of that at your disposal, so you can see what's actually occurring and what we're seeing as well, and you can get a good idea for all of the information that we have available. Now, if you go to our webpage, also on the bottom left here that you see is called a weather story. So when we are putting together our forecast for today, we will make a graphical weather companion piece to kind of let you know what we're looking for. So that'll kind of let you know what we're watching for that day. In this case, it's severe potential. It could be something in terms of marine weather or winds that are developing, or whatever that piece of weather information that we need you to know about is. You're going to see that on our webpage. And that's a good way to kind of get that information quickly. We'll give you the key points, actions you might need to take, any potential information that we need to make sure that you have access to. And this is available, again, we update it every day, early on in the morning, typically by 6 or 6:30 in the morning, and then in the evening as well. So you'll have that information at your disposal. Also linked on that page is the forecast discussion. And this is a little bit more of a technical product. It will kind of go into what it is that we're seeing in terms of the forecast rationale, what we're looking for, what we're watching. We'll get into probabilistic information, what's the most likely outcome that we're watching for, what's the expected impacts, things of that nature, a more scientifically based discussion. For those who want more information, this is that additional information that we kind of pass along to let you know what it is that we're seeing. Again, on the bottom there, you can kind of get into the more sciencey nuts and bolts of the forecast if that's something that you desire. If not, you can go ahead and kind of go past it. But sometimes we find that folks want the more nuts and bolts of what it is that we're seeing, and that's how we pass that information along. For the more quick hitting information, we have this graphical hazards icon on our webpage here in the upper right. You can see that on our webpage. And this graphical hazard will typically break down the threats that are available. This is the graphical HWO. So the graphical hazardous weather outlook will kind of outline what we're expecting to occur. And the limited risks, elevated risks, significant and extreme, all those will be broken down on this page. So in terms of each individual weather element, it'll be delineated on that graphic what that means. So when you kind of click on it, you can kind of say in case of wind, that'd be breezy conditions. For orange, it'd be elevated winds. For significant, 50 to 60 mile per hour, and so on. So for the next section, we'll get into watches and warnings. And again, we had a question about that. And when we get into severe thunderstorms that you might see moving through your area, you might see a watch is in effect. And that severe thunderstorm watch is issued by our office. But when we have those out, we're looking for specific criteria. And that's something that some folks don't really think about is there are specific criteria for severe thunderstorm. It's not just something we say this storm is severe and this storm's not. We're looking for 1-inch hail and or 58 mile per hour wind gusts. So we're looking for a storm that produces either of those or both within the confines of that storm. We don't issue warnings for lightning because obviously lightning is something that is inherently part of any thunderstorm. So we'd be issuing warnings for all thunderstorms, which is something that we don't want and you don't want, because that'd be something that we'd be warning for all storms, which is not really helpful in our mission. It's not going to help you any to kind of get warnings for every thunderstorm that moves through the area. Now, in terms of watches versus warnings, conditions for a watch are when we're looking at conditions being favorable for a particular hazard in and near the watch area. In this case, tornadoes or severe thunderstorms. We're watching ingredients come together, essentially. This is going to be issued by the Storm Prediction Center in Norman, Oklahoma. So they'll chat us up via our chat bot internally here, and we'll kind of get that notification from them, and we'll kind of figure out which areas are going to be in the watch versus not, and that will go up for several hours at a time. And we're looking at certain factors for the watches, and we'll talk about what those factors are as we go forward here. But typically, this is going to be for several hours at a time for generally a pretty large area. And again, you'll get these graphics on our social media feed. Typically, it's going to be on X because these are more time sensitive. We'll talk about this as we go forward as well. But typically, when you get into Facebook, Facebook algorithm is such that you might see this 3 days from now, which is not going to be helpful for you from a severe weather perspective. So we try to keep things time sensitive on X so you can see the latest information in a time sensitive way. The warnings are going to be when we are expecting weather that is imminent or happening now. So when we're looking for something that's happening, this is issued by our meteorologists here in Wakefield. And that's going to be for our entire forecast area. And that's going to be when we're expecting that weather to be occurring. So it's happening now or it's about to happen. And that's the threat there. And the polygons that you see here are going to be based on the area of the greatest threat. We have a question here. Do all warnings start from the guidance from Storm Prediction Center, or do we issue those? We will issue those. So all of these warnings are going to be issued by our meteorologists here in Wakefield. The watches are going to be issued by the Storm Prediction Center. The warnings are all by our meteorologists and every National Weather Service forecast office that for their local area. So as far as our area is concerned, we're issuing all of these warnings here locally, internally. Put simply, if you're watching for ingredients for tacos, we'll put it that way. You look at all the ingredients, your meats, your vegetables, your tortillas, your cheese, your lettuce, all of that ingredient. When you have those, you're in a taco watch. When you're getting into a taco warning, you have all of those ingredients ready to go, and you're having tacos right now. So put simply, we're watching ingredients come together on the left. When we have a watch phase, we're watching ingredients come together. Maybe the shear is moving together versus the instability versus the moisture. Maybe we're waiting for some of that to happen. Once it does happen and we have mature thunderstorms, we're getting into tacos and we're getting into thunderstorms. So hopefully that makes it a little bit clearer. So this is a good time to ask or kind of think about, I guess on your end, how you receive warning information. There's a lot of different ways to receive warnings out there. And typically you'll hear us say to have as many different ways of getting that information as possible. So in terms of your wireless emergency alerts on your phones, we're going to have that available on the next slide here. We'll talk about those. Your favorite television or radio station that you have, that'd be fine. Your favorite internet site or mobile application, that's great. I would say have as many of those as possible because things break, right? You might have a favorite weather app that works. Maybe make two or three that you know work and can give you the proper information. NOAA Weather Radio, certainly. That's a great source to have that information. Immediate broadcast of watches and warnings on NOAA Weather Radio. And if you program your county code in there, the radio will alert itself and give you that information when we issue warnings. Weather apps, you see the FEMA app there on the slide there. Pick your favorite app. The Red Cross app is also out there. Other apps that provide that information automatically, really good things to have. And if your county has a warning system that provides you that information automatically, so much the better. So about these wireless emergency alerts. These are emergency alerts that are sent by us and the Weather Service, in this case, to your mobile device. So these alerts are going to be sent without needing to download anything, without needing to subscribe to anything. They're just going to be sent to you. So you'll get those in case of extreme weather warnings from tropical systems, local emergencies, or amber alerts or things of that nature. And that's going to be something that will tell you, hey, we're looking at a tornado moving through. We're looking at a particularly severe or dangerous thunderstorm producing 70 to 80 mile per hour wind or greater, or larger than 2-inch hail in diameter hail. You'll get those emergency alerts in those cases. We try not to get you those alerts in every case because we don't want to just make sure that, we don't want to make every warning the thing that sets your phone off. But if we issue tornado warnings, if we issue a catastrophic emergency alert for a thunderstorm that's, again, greater than 2-inch hail in diameter, greater than 70 mile per hour wind, we're going to make sure that you have that information because that's important. And we want you to be able to take shelter. So in terms of getting this information, go ahead and you can check these out in terms of your particular mobile device. Be able to go in and look at what's available on your mobile device. Make sure they're checked on to receive emergency alerts and public safety alerts, because that's important in terms of getting that information. We have a question. The warnings go through radar scope. The warnings absolutely do go through radar scope. So you'll be able to get that information through radar scope at all times. So you'll have access to that if you use the radar scope software. In terms of thunderstorm meteorology, and we'll get into some of the ingredients here for thunderstorm meteorology. Typically when we start to get into the spring and summer months here, when we get into the warm season, our air starts to get heated by the sun. And the sun doesn't directly heat the air. It heats the ground. The ground, in turn, warms the air around us because that warm air will heat the ground. Warm air rises. As warm air is less dense, it will typically start to become less dense and rise. This is known as increasing instability. So we start to increase the instability when we heat the ground, and that ground, in turn, warms the air around us. It's like putting heat into a balloon or heating water on the stove. That's how we get that instability cranking up, is to add heat. Now, in the presence of enough moisture, and we have a lot of moisture sources around, we've got the Gulf moisture, we've got the Bay moisture, we've got the Atlantic moisture coming in off the ocean. That is going to allow, in most cases, the lift to basically manifest in the case of clouds that are developing. And with updrafts getting going, the updraft will be our warm air pushing up. When that happens, we can develop a towering cumulus cloud. We're basically going to stretch our clouds in the vertical. So we're going to start to elongate our clouds in the vertical, make towering cumulus clouds. So those cumulus clouds are those puffy cotton ball clouds from our science class that develop during the heat of the day and start to pop up. And as our warm air starts to lift up and really get going and gets that instability cranking, we can start to elongate those clouds in the vertical, get towering cumulus clouds, and start to really get that instability farther and farther up into the atmosphere. Now, what really kickstarts that process, really puts this process into overdrive, is to get a source of lift. Now, in this case, we're talking about any number of factors. For today's purposes in basic SKYWARN, we're going to be focusing on fronts. But we have a special case of sea breezes, which is basically a front coming in from the ocean. So basically the sea breeze is kind of the same situation where we have kind of a light wind, and the cooler ocean water basically will make a front that pushes inland toward the warmer land areas. So in either case, we're basically taking cooler air and pushing it towards the warmer air and forcing it upwards. And as that happens, we're going to accelerate that lift and kind of really get that updraft process kick-started. So when we have a mature thunderstorm, we have a fully symbiotic relationship between the updraft there in the yellow and the downdraft there in the green. Now you'll notice in the updraft area, we have a clearer sky behind it. It's brighter. It's brighter because there's no rain there. We call that the rain-free base. And the rain-free base is named such because, surprise, there's no rain there. That's all air going up into our thunderstorm. The air is lifting up into our thunderstorm. So as that happens, we're going to start to lift our warmer air up into our thunderstorm. If we have a 32 degrees Fahrenheit line, 0 degrees Celsius, this is going to buckle upwards because we have warmer air buckling upwards into the farther up into the sky. Now that upwards momentum is going to continue until we get to a point where the lift is the same temperature as the air around it. And as that warmer air starts to encounter colder air aloft, that lift is going to tend to slow down or stop. And that level at which it stops will tend to be what we call the equilibrium level, or EL. And that equilibrium level tends to be where our instability goes away. We go back towards more stable. And then at that point, inherently, our air is going to start to make its way back down to the ground. We can't destroy energy, as Newton tells us. So all of this air has to make its way back down towards the ground. And this is rain-cooled air in the downdraft portion. This is going to be downdraft, where the air is moving back down towards the ground. That same line, 32 Fahrenheit, 0 Celsius, is going to be buckled downward in the downdraft region because all of our cooler air is coming back down. So in the downdraft area, this is going to be buckled towards the ground because our cooler air is coming down. So in the downdraft section, here in the green, it's a darker sky because we have air moving towards the ground. We have our rain moving towards the ground. Thunderstorm outflow, all of our wind, all of our heavy rain, it's going to be in the downdraft section. So this is where you're going to be able to see your rain shaft, and you're going to be able to see a lot of that action moving towards the ground because that's where all of the action is moving towards. So we've got our three ingredients. We've got our moisture, we've got our instability, we've got our lift. The fourth ingredient, or 3B, I guess you would say, is wind shear. And wind shear is needed to keep the updraft and the downdraft separated from each other. We're going to need to keep the updraft and downdraft apart. And the reason for that is we need to keep them separated away from each other because if they kind of come together, they'll tend to cancel each other out, which will be basically will end up in our storm falling apart. So there we can describe wind shear in two different ways. Number one, we have speed shear. That is basically an increase of wind with height. Next, we have directional shear. That's going to be a general veering of the wind from easterly at the surface, east-southeasterly at the surface, say 5 or 6 on the face of a clock as you're looking at it, versus the top of our storm, which might be 9, 10, 11 o'clock on the face of a clock as you're looking at it. So that veering of the wind is going to produce the same type of phenomena. So what that results in is kind of a tilting look to our thunderstorm. This is what it would look like in terms of a veering wind profile. And this is what a speed shear would look like, just the increasing wind with height. And the result is going to be a tilting storm. And why is that important? Because in this case, our updraft in the yellowy arrows are going to be separated from our downdraft in the blue arrows. If that doesn't happen, if our storm is basically the updraft and the downdraft are basically right on top of each other, what happens is the storm doesn't really have any warm, moist air keeping it going. Ergo, the storm basically collapses on itself and dies. So basically, if we don't have that shear, our storms are going to collapse very quickly. And it's something that, if you don't have that, you're not going to have the ability to keep our storms moving. So here's our type of thunderstorms. We have single cell or fairly short-lived. They can produce typically lower end threats, but they can produce the lightning and heavy rain and smaller hail. As you get into the multicellular clusters, these form with numerous cells that move together. They're typically can make a difference in how much area an area would receive, and they can produce some larger hail. Typically, this will be in multiple stages of development. You might have a storm that's mature next to a storm that's falling apart, next to a storm that's just developing. So you can have storms in different stages of development with the clusters. The squall line is a majority of our severe weather cases. They can extend for hundreds of miles. They can persist for quite a while and produce wind and hail. Typically, these will be along fronts as they move through. And the supercell are responsible for almost all of the tornadoes in the United States. They produce extreme winds, flash flooding, and large hail. Typically, they're not going to be everywhere, but where they're present, they're going to produce severe weather. So let's break them down here a little bit. The single cell is going to be kind of a storm on its own, kind of a small hail threat, gusty wind threat, maybe some heavier downpours. In and of itself, not really much of a threat in and of itself. The supercell is going to be something that is producing some pretty dangerous conditions, large hail, gusty winds, potentially a tornadic wind, heavier downpours. The squall line, what we call a quasi-linear convective system, QLCS, you might hear that term occasionally. Basically what that means is you have a long line of storms moving through. And the wind will tend to come right out of this thunderstorm, typically at the apex of the bow. If you kind of bend this, if you look at this, it's kind of like bending a bow and arrow back. And at the apex of the bow, where it juts out the most, that's where our greatest severe weather threat is going to be, right in this area. And then the mesoscale convective system, we call that an MCS. That tends to be with a strong upper level disturbance that comes through. And again, at the apex of the bow, you can start to see this reflectivity is a little bit weaker. That tends to be where the strongest wind is starting to peek its way through. So at the apex of this bow, it's where our strongest storms are going to be. So this is a squall line in motion. You can kind of see, again, this is from the Carolinas, the Virginias, all the way through the Carolinas and into the deep south. So it's a pretty large area that winds up getting covered by this. So you can kind of see the threat the squall line can present and the amount of area that can be threatened by a squall line. Primary threat with the squall line is going to be damaging winds. You'll see a shelf cloud. The shelf cloud is going to be what is going to be noted with the squall, because the squall line will move through as a front, and you'll have that airflow moving up into our thunderstorm, and then as the storm moves through, the wind turns back around and then blows at you. So as you're watching the storm approach, all of this wind in this picture is blowing towards this storm, until that storm comes up and moves through your location, at which time the wind turns around and blows through town. It kind of blows out of our thunderstorm. And that is called the gust front. When you kind of think of a thunderstorm coming through, you think about that cool burst of wind that's moving through. So basically, that's going to be a determination of that wind coming out of our thunderstorm and blowing through. That's going to be that cool burst of wind that our storm is producing as it's moving through. So the wind out ahead of it's going to be inflow, and then the wind moving through it is going to be the outflow. The worst will be first heavier rain, followed by gradually decreasing wind and rain intensity. I had a question here: is the wind speed determining the intensity of the precipitation, or how fast the storm is moving across the area? The wind speed is going to be a reflection of how much wind is descending toward the ground in the downdraft area and then moving through. So if you have a stronger updraft, stronger downburst, that's going to produce a stronger outflow. A weaker updraft, a weaker downburst is going to produce a weaker outflow. So here's a picture of a squall line and a gust front blowing through. And this is going to be kind of, watch this co-op center in the center of the screen here. All of this wind is pulled toward our thunderstorm until the squall line develops. And then the squall line quickly develops and the storm moves through town. And now as the storm is moving through town, all of that wind turns around. Here comes the dust. And the dust is going to blow through, kind of tell you the wind is quickly turned around. So all of that wind is going to go towards our thunderstorm until that thunderstorm moves through town. And when it does so, that wind's going to quickly turn around and blow through our location or your location as you're experiencing this thunderstorm. So here's our thunderstorm section. This is for supercells. This produced some pretty large hail in the Richmond area in 2017. And all of our supercells are inherently more dangerous because of the fact that we have enough of the shear that is present that is going to make it so as the storm moves through, it's already rotating. Before we get to severe limits, the storm itself is already rotating. So that's going to add an extra element of danger there. So we have the ability to make a quick spin up of our storms. And then at the top of our storm, you'll tend to see what we call an overshooting top. And the overshooting top is going to be this little cap on top of the thunderstorm. And that cap on the top of our thunderstorm is going to kind of tell you that you have a very, very strong updraft. So basically, as our updraft is going up into our thunderstorm, as I said earlier, you'll tend to have an equilibrium level. It's the top of our thunderstorm where our equilibrium returns and our stability goes back to more stable versus unstable. Well, in the event of a very strong vertical velocity, in the event we have a very strong updraft that's really, really moving in the vertical direction, moving up into our thunderstorm, that vertical velocity is not going to be able to stop. That updraft is not going to be able to stop. So it gets to the top of our storm and it busts through that top of our thunderstorms. Think of busting through the roof of a glass elevator, or thinking about busting through a glass ceiling. You're going to kind of get all of that moisture and lift up above the top of our thunderstorm. And in so doing, you're going to produce this overshooting top. And that's going to tell you we have a lot of lift available within this thunderstorm. And of course, what is going up has to come back down. So when you see those overshooting tops, that tells you that you have some very intense lift that you need to contend with for those thunderstorms that you need to watch out for, which could mean strong winds, which could mean very large hail, which potentially could produce a tornado. But for the most part, you're looking at stronger winds and a hail threat. Now you'll note the anvil here. The anvil is your meteorological neon arrow. And as you're watching the anvil develop and move through, that's kind of telling you that our updraft will take our updraft, and then it'll kind of get smoothed out ahead of our storm. So the anvil is going to tell you the direction in which the thunderstorm is moving. So the anvil will point which way the thunderstorm is going. In this case, the thunderstorm is going from the right towards the left. So you can watch our thunderstorms move through and get an idea for where our storms are going just by watching that anvil. So again, in terms of the supercell, again, you're going to want that rotation evident within the updraft. So we're watching the rotation within the updraft. So again, what you're going to see with respect to our thunderstorms is going to be different depending upon where you are. This forward flank back in here at the top, that's going to be mainly heavy rainfall. The supercell is going to be in this quadrant, which is typically going to be where our tornado is going to end up, back in here. So where your location is going to be kind of an indication of what you're seeing. If you're in location A, getting dumped on by all this rain, you're probably not going to be able to see much around you. If you're in location B or C, you're going to be able to see a lot of this detail in this portion of the storm, in this portion of the supercell. Now, with respect to hail, the stronger the updraft, the larger the hail. Really, that's the fundamental fact there. And the more moisture you get above the freezing level, 0 degrees Celsius, 32 Fahrenheit, the more you take this moisture and you lift it up above that freezing level, the higher up you get it, the larger the hailstones are going to become. Because the stronger the updraft, the longer those hailstones can be supported and held above that freezing level, the more they're going to kind of bounce around. And you can kind of think about that as like the little ping pong balls on the evening lotto drawing. You can kind of think about those ping pong balls on the lotto drawing because they're being held up by air. The updraft with the hailstones is kind of the same situation. The hailstones are kind of bounce around within our thunderstorm, being buffeted and being held up by our updraft. And if we have a strong updraft, a really strong vertical velocity pushing up in the vertical, we're going to be able to support the weight of those hailstones that are becoming larger and larger, picking up moisture and freezing. Now, when we get to the point where the updraft can no longer handle the weight of those hailstones, it will then drop them. And at that point, that's when you have a hailstorm, is when the updraft can no longer handle the weight of that hail that it was suspending in the air. So that'll typically be where a typical location where a town or two will wind up getting buffeted by large hail because the updraft just can't handle the weight of the hail any longer. So the dangers of hail are pretty straightforward, I would imagine. I would hope. You have damage to vehicles, potentially with large amounts of ice falling from the sky, crops, structures in terms of home damage and siding damage, roof damage. It can also produce dangerous driving conditions because essentially it's just ice falling from the sky onto the road. So even lots of pea-size hail can cause problems in terms of navigation for sure. So in terms of rotating updrafts, again, these updrafts can support some very large hailstones. This is the largest hailstone recorded here in the CONUS. It's 2010 in Vivian, South Dakota. Tail of the tape on this guy, 8 inches in diameter, a little more than 18.5 inches in circumference, and almost 2 pounds. So quite a bit of heft on this hailstone, just a little bit bigger than volleyball size. So very, very impressive hailstone with that occurred in 2010. So the dangers of hail, obviously pretty straightforward, I would imagine, in terms of that. Let me just lower the volume on that. And you can kind of see the hailstones falling and get that indication of all this hail. Typically, you're going to want to report the largest hailstone from this. So we want you to be safe, obviously, but by all means, report the largest hailstone you see. Try to relate it to the size of a ball or a coin, if at all possible, so that we have a recognizable reference point. Next, we'll talk about wind. And wind is the majority of our severe weather cases here in the mid-Atlantic. And in terms of the straight line wind, this is when we're looking at wind that is not directly associated with tornadic circulation. So when we tell our spotters and we tell folks that call the office that their wind was a microburst or straight line wind damage, we're not diminishing the intensity of the damage that occurred at your location. We're simply saying that it wasn't tornadic. So certainly straight line wind can mimic EF0, EF1 type tornado damage. And we'll talk about the Fujita scale in just a little bit. But even lower end tornado damage can be mimicked or imitated by straight line wind. And simply that is thunderstorm wind coming out of our thunderstorm and making impact with the ground. So if I were to pour water out of a bottle of water onto the table, it would hit the surface of the table and spread outward. And that is what air is going to do, because air behaves like a fluid. So basically, as that impact occurs, that is going to produce a downburst, and there down the line would be a squall line or a gust front. So once it makes impact with the ground, it's going to hit the ground and then diffuse outward. So the main impact of damage, the strongest damage, is that going to be a fairly small area? Yes, it'll be a very small area that gets impacted by the strongest wind. Will there be additional damage that spreads out, emanates from there? Absolutely. So that's why we call it a downburst. It's going to make the most damage in a very small area, which will then diffuse outward away from that point. So here is a downburst that occurred in Columbia, South Carolina. And you can watch the center of your screen here and watch this updraft move on through. Right there. And you can see the impact occur right in the center of that screen. And then once it makes impact, it'll diffuse outward. So in the center of the screen there that you see, that's where the most damage occurred. Additional damage occurred on the other side, on either side of that, from that wind kind of diffusing and spreading out. But the worst damage absolutely is going to be in a very small area, a couple of miles at the very most, is going to have the worst damage. Now you're looking at downburst damage. We have what we call a divergent wind path, which is to say that our wind is going to just go straight out and just diffuse out, just kind of like these lines would never meet theoretically. And it's going to produce damage like this, where it's kind of like a bunch of dominoes being knocked down. It's all lying in the same direction or very similar orientation, because all of that wind is going to just push through and knock everything down. Our squall line quickly moves through, so it typically will move through very fast, produce a bunch of damage over a large area, and the winds will gradually weaken. Now, especially when you look at radar and you'll start to see these narrow lines out ahead of them, this is the outflow. This is the actual thunderstorm outflow moving ahead of our thunderstorm. And that will tell you, this is your indication that our winds are moving out ahead of our thunderstorm. And when that happens, that means our storms are going to gradually weaken, because the winds will start to really kind of move out ahead of our thunderstorms and be able to move out ahead of them. And our storms will weaken because they don't really have the forcing to keep them moving through. And as we talked about a couple of slides back, the bow echo is your indication of enhanced wind damage. And at the apex of that bow, in the case of storms moving southwest to northeast, as you see here, the apex of that bow is going to be where the strongest winds are going to be. As you bend that bow and arrow back, at the apex of that bow, at the most protruding part of that bow, that's where the strongest winds are going to wind up being. Which brings us to the derecho. The derecho is a long-lived organized thunderstorm complex. Now, in terms of the aerial coverage, there is an aerial coverage component to the derecho. We need a damage swath of greater than 240 miles. So that's what's going to make it determine whether it's a derecho or whether it's just an MCS or whether it's just thunderstorms moving through, is whether it's impacting that much area. Now, with a derecho, a telltale sign whether it's a derecho or not will be whether it's occurring in a very hot air mass. Back in 2012, which you see this air mass that produced this derecho that moved through our area, we had temperatures well into the 90s to low 100s, heat index values around 110. This was a very warm day. So those storms moved from Chicago through Richmond in a matter of 12 to 14 hours. So these storms were hauling pretty good as they were moving through. But the derecho itself will typically be found in a very, very warm, humid air mass. Now, in terms of flooding, we have flash flooding being defined as the rapid rise of water onto previously dry areas. So that could be from water going over the banks of a river, or heavy rainfall just kind of pooling in an area because of poor drainage or an urbanized area. Or it'll just be something where the water just very, very quickly rushes through as a result of a dam break. So any of those factors could produce flash flooding. The force of a flash flood can move homes or cars, especially in the case of the homes not being secured to the ground in any way. We can very easily move homes that are not secured to the ground. Certainly just less than 2 feet of water can float a vehicle, and 6 inches of moving water can knock you off your feet. So the power of moving water is very, very strong, which is why we tell folks to turn around, don't drown, because once you're impacted by that water, you're going where the water wants you to go, and we don't want you to be in that situation. In terms of watches and warnings, once again, as we said with the tacos earlier, a watch is when we're watching the ingredients coming together. A warning is when that flooding is happening or it's about to happen, and you need to move to higher ground in those cases. And we say never drive through flooded roadways because we don't want you impacted by that water. So by all means, turn around, don't drown. Make sure you're safe from that flood water. Now, with the tornado, we have the ability to issue what's called a flash flood emergency. And this would be when we're issuing flooding warnings with an extremely high risk to life and property. Example of that is back in 2018, we had 9 inches of rain in 2 hours over portions of northeastern Maryland, which produced flooding that you see here. So again, a very good example of why we would need a flash flood emergency in this type of situation. Now, for less urgent, more typical flood conditions, we would have what's called a urban small stream flooding, or perhaps a more aerial flood warning. And this is for typically, in the case of small stream and urban, for flooding where we have standing water on the road or stream out of its banks. More typical flooding of underpasses or typical flood-prone areas, typically not life-threatening flooding. These will be something like this, or this, or this. You'll get a message through our social media feed on X, where you'll see that pop out there, and you can get that information very quickly in terms of what we're expecting and where we're expecting it to go. 3 basic things for flash flood safety. You want to get to higher ground. You want to turn around and not drown. We don't want you to get into a situation where 6 inches of water knock you off your feet and you're in the flood water at that point. We don't want that for you or your family or anyone really. And then obviously stay informed of the latest conditions and be ready to move where you need to go to higher ground to keep yourself safe and your family safe. All right, our second part here, and we usually take a break for this part of the presentation. So feel free to give yourself a break if you'd like to take yourself a break. But here in part 2, we talk about tornadoes primarily, and we will talk about tornadoes with the Fujita scale. The Fujita scale is again an ascending scale from 0 to 5. From up to 85 mile per hour wind and minor wind damage, up to EF5, which is severe, extreme, or incredible damage with respect to what's actually occurring. Now, this scale was remade back in 2005, 2006. Basically, some research meteorologists went back with NOAA and with the insurance industry to kind of figure out how to look at the Fujita scale to quantify damage versus just quantifying how strong the wind was. And what was actually done was we came up with what are called damage indicators, so that our meteorologists looking at our storm damage can actually look at something scientific to say, you see damage here to this school, to this home, to this building. What kind of wind damage will be required to produce damage of that sort? And we have damage indicators, hundreds of them, that would kind of indicate, to see something like this, what you would need is X amount of wind. And our tornado survey teams have this information that they can very quickly access and have information at their fingertips to figure out how strong that wind would be to create the damage that they're seeing. Now, in part one, we talked about the shelf cloud. That's that cigar-shaped cloud on the leading edge, kind of like a paper towel roll rolling across a table. In this part of it, with respect to tornadoes, we're looking at the wall cloud. And the wall cloud is an isolated lowering of the cloud base, typically at the base of the updraft. So you look at the base of the updraft, you see the rain-free base back here, brighter sky. And basically, the updraft is ingesting the rain-cooled air coming out of the downdraft region. So as a result of that, because it's taking in that cooler air, the wall cloud is typically going to be pointed towards the rainfall area. So you'll be able to see that, that feature pointed towards the rainfall area. Now, this feature will be rotating as it's moving. So you'll start to see that rotating updraft implied in there, because what you're seeing is this wall cloud spinning. So that updraft plus the rotation is something that you need to monitor for a tornado. Now, this is the West Liberty, Kentucky tornado from 2012. This is going to be accelerated for visual effect, so you can kind of pick up on all the features. Generally, just kind of consider that if the base of the wall cloud is rotating, so is the updraft. So we're going to watch the wall cloud in the center of the screen there. We're going to watch the inflow coming in from the right. We're going to watch the outflow coming around the left side, and that's going to create the tightening of that circulation. Now, like a figure skater that brings his or her arms in closer together to rotate tighter or to turn tighter, so too does this circulation, the inflow and the outflow, rotating faster produces a faster circulation. So that rotation will tend to be counterclockwise in the northern hemisphere unless it's being forced another way by another feature. The tornado will drop down from the bottom, typically in the center of the wall cloud. It will drop from underneath there, and you'll see the tornado lowering to the ground. You'll see the funnel lowering, and then the tornado itself will be the tornado on the ground. And the updraft goes up over the top toward the anvil. So let's put all of this into motion. And you can see the circulation coming around the side from the right, turning around the left side. Kind of watch it again. You can kind of see that circulation kind of tightening up. And the tightening up is the result of that circulation becoming tighter, because the updraft and the inflow and the outflow are kind of tightening up that circulation. So the key to spotting the wall clouds is going to be twofold. Number one, as you watch this picture in the screen here, you're going to be watching for a sustained upward motion. As you're watching this picture evolve, it's going to be persistent. It's going to be something that's continuing on. Initially, it was not part of the wall. It was not part of the storm base, and now it is. So you're watching that feature continue on and continue to blow and continue to rotate and start to hook up with the bottom part of the storm base. Next is the vertical axis of rotation. Now, in the first portion of it, we were talking about the shelf cloud, which is the horizontal rotation, that horizontal tube of air rotating. Well, now we've got enough shear that we have actually taken that column of air and we've actually turned it on its head, and we're actually now rotating in the vertical. So we're taking that updraft and we're lifting it up into the vertical, up into our thunderstorm. So the vertical axis of rotation is now what we're seeking. We're looking for that rotation going upwards in the vertical. So the shelf versus the wall, very simply, is the shelf cloud is sloping away from the precipitation. The darker clouds are sloping away towards the updraft, the brighter area. This is indicating downdraft or outflow. This is the storm pushing air out. Think of the storm pushing air out. The wall cloud is going to slope towards the precipitation area. That is the wall cloud kind of taking in that rain-cooled air getting pushed out of our shelf cloud area. So it's kind of taking in that outflow. So it's going to indicate updraft or inflow. It's taking the air in and it's pushing that air farther up into our thunderstorm. So the slope is going to be towards the precipitation area. So the rain-free base is going to be sloped towards the precipitation in this case with the wall cloud. So funnel cloud versus wall cloud is very simply, the funnel is a cloud extending downward from the base that's attached to the cloud base, but it's not impacting the ground. You're seeing no impacts on the ground level in this case. So you're going to see a rapid rotation here in the funnel. It might be laminar or smoothed out. The wind kind of rotating around it is going to produce what we call striated air, which is going to make it kind of smoothed out. We're kind of sanding it down, if you will. We're kind of making it really, really smoothed. So you can kind of just see that that funnel kind of really smoothing out in terms of the appearance. The tornado is not only that rotating column of air, but it's in contact with the ground. Now, you might not see the condensation funnel itself impacting the ground, but take a look at this picture. What you're seeing is damage. What you're seeing is something getting kicked up, be it debris, be it something, be it trees, leaves, home debris. Something is getting kicked up to produce that damage. That's what I want you to key in on, is that damage. Not necessarily the funnel itself on the ground, but damage being visibly done on the ground. You can see, depending upon how good your picture is where you are, there is damage getting kicked up and debris getting kicked up here close to the ground level. And that debris getting kicked up, that damage visibly being done, that's your evidence that there's a tornado on the ground. So spotting tornadoes, very simply, it's going to come down to analyzing rotation toward the ground. Very simply, seeing that damage is going to be your proof. Some tornadoes are going to be kind of rope-like or skinny looking. They're all going to be tornadoes. So whether it's kind of more picturesque looking like the one you see here, whether it's kind of uglier looking like you see something like this. This is from Maine a couple years ago. But something like this, it's not the most picturesque, pretty thing in the world. There's no Hollywood magic here to make this look like a pretty tornado, but it's still a tornado. So you can certainly look for that vertical motion, more rotation. That damage visibly being done is your proof that you have a tornado on the ground. So seeing that is your proof. Some more specialized cases here. You're watching our storms moving through, but you're not seeing any rotation. Just kind of keep an eye on this here. And as you see these clouds kind of sitting here, you generally would ask yourself, do you see rotation? Maybe if you call this in to the Weather Service, you'll ask us about the tornado that you're seeing, and we'll ask you if you see rotation. And in this case, you'll obviously say no, because you're not seeing rotation. You're seeing clouds just kind of sitting there. And this is what's called scud cloud, S-C-U-D, scud clouds. And that typically will mean that they're just kind of scary looking clouds. We call them scary looking clouds as an alternate name is scary looking clouds. They just kind of sit there. They're not doing anything. They're not bothering anybody. They might be scaring some people, but that's pretty much all they're doing. We'll ask you to keep an eye on these. Make sure they don't start to rotate. Make sure they don't start to very quickly change shape, because that could be an indication of something else. But as long as they're just sitting here, this is what we call convective debris. They're just sitting there, just minding their own business, not doing anything. Now this, on the other hand, is just kind of watching a storm one day, and very quickly it can escalate very quickly, which is what you're seeing here. The storm very quickly descends to the ground, very quickly produces a tornado, and very quickly is making damage. So that kind of information can be very important to let us know what it is you're seeing. Make sure you're safe, obviously, but this is something that we need to hear about. In terms of squall lines or tornadoes, this is what we call a QLCS that is basically rain wrapped. When we say rain wrapped, we say that this line of storms produce a weak tornado, typically EF0, EF1, but it can be in some rare cases EF2, EF3. But the most important thing is they're going to be rain wrapped, because they're basically being enveloped in the heavy rainfall and obscured by the heavy rainfall, such that when you see this line of storms coming, you're not going to see the tornado. You're just going to see dark clouds and heavy rainfall. So they're going to be very, very difficult to spot. And it's something where let us know about what you're experiencing, because that extra little bit that you experience with that will be something where we can issue a warning farther on down the line, for that as this storm impacts additional communities to your east, we can let folks know, hey, there might be a tornado in here. And this storm might be on the ground for, this tornado might be on the ground for 15 to 20 seconds, and the radar will never see it on the ground. So it's something that could very quickly do damage like this, move on its way, and be done. And that's something that's, unfortunately, the radar is not going to be able to be helpful in those cases, because it's on the ground for such a short period of time. Here's an example of a rain-wrapped storm that's on the Chesapeake Bay. And watch this storm as it's rolling through here. There it is. So you can see the elements of the tornado in there on the water spout there on the bay, and it really, you had to look at it for a couple of cycles, look at it for a few minutes to kind of get the idea that it's there. You kind of have to get really close to those details before you can actually see it, which is what we're talking about in terms of, those elements are something that's going to be known to you only until they come closer and you're able to really see those details. So when you see those uncertainties, what happens when you're not sure of what it is you're looking at? We say to report it anyway. I'd rather have some information than no information at all. I'd rather you be safe than sorry in that case. I'd rather to have that information versus not. So report what you're seeing. Don't give generalizations. Don't make assumptions. Instead of saying I see a funnel cloud, say it's a possible funnel cloud, because it's close to attached to the storm base. It's been persistent. It's too far away. And folks, we live here too. We're from the local area too. We know the tree line is a pain in the butt. I mean, we get it. So if you say, this is what I'm seeing, but the tree line's not allowing me to get a good look at the lower levels, we get that. We understand that. Just report what it is that you're seeing, because I'd rather have a partial report than no report at all. So some folks think about our operations area, and they think we have lots and lots of resources and lots of folks to lean on and report to and get information from. And Nope, not us. This is Mission Control down in Houston. They have a lot more folks at their disposal than we do. We have 2 to 4 meteorologists working at a time. We might be able to get 8 to 10 folks working during severe weather, but typically this is going to be something where, time is going to be of the essence. We're going to need to get as much information as we can get as quickly as we can get it. So if you're calling us, number one, please call us if you have information to report. But realize that we might be able to talk to you for only 30 seconds to a minute or two at the very most. And we're going to have to move on to the next person that calls or move on to our next thing on our list. Please don't take that as a reason not to call because we definitely appreciate our spotters, but we might not have the ability to chat at that time. So realize the time may be of the essence for us, and please don't take that personally. We very much appreciate all of our spotters. A question we often receive is, do we offer tours? And we do. Typically, it will be during business hours, Monday to Friday, but we will try to make that work for groups of 20 or less. If you go to the local programs section of our webpage, you'll be able to pick a drop down there and pick up a time for touring the office if you are so inclined. So if you are interested, feel free to check that out. In terms of reporting to us, by all means, identify yourself as a spotter. We no longer issue IDs, so you don't need to tell us your spotter ID number if you don't have one. By all means, just kind of tell us your location as best as you can relay it. 5 miles west of Wakefield or south of, the intersection of 40 and 460. If you have latitude, longitude information, that's great. Typically, we have amateur radio folks that know their latitude, longitude down to the thousandth decimal degree. You don't need that information. If you have it, that's great. I'm not going to hassle you if you don't know it. But I will say, if you are watching a cloud feature or a persistent cloud feature, try to keep an eye on which direction you're looking. As far as the time of the event, provide a start and end time if you're watching something for a long period of time. It's a good practice to get into. And also, if you can have a compass available, either a physical compass or a compass on your cell phone, where you can just figure out which direction you're looking in, that is eminently useful for us, because we need to get that information in terms of which direction you're looking, and that's a little bit more difficult here because we don't have the grids that they would have in the Midwest. So kind of get those compasses, get a good feel for which direction you're looking in, and that's really helpful in terms of telling us which direction you're looking in. For the event itself, I'm not going to go through all of this. It's in the handouts, but typically hail, damage to trees, 40 mile per hour or greater. Any of this stuff is important in terms of giving us information. You don't need to report lightning. We have a lightning network at our disposal. But also, if you report something really higher end, like a tornado or a strong thunderstorm producing large hail, please don't be put out if we ask for your contact info. We're not trying to monitor you or anything. We're just trying to get more information about what it is you saw. So if we ask for contact info, please don't be alarmed. We're not trying to do anything more than just get more information. This is your hail site. Here again, report the largest hailstone that you see. So if you see a couple of quarters and some pennies or nickels, go ahead and report the quarter. If you see larger hail, go ahead and report the largest one. Only thing I ask is please don't report marble size hail, because I don't know what size marbles are in your world. And it's not really universally recognizable. Try to relate it to the size of a ball or a coin, or something easily recognizable. In terms of reporting wind, realize that measuring wind is hard for everyone. That's professional meteorologists, that's spotters, that's everyone. Wind speeds are going to be hard to estimate. They're difficult and they're prone to error. Measured wind speeds will always take precedence. I went the wrong way. Measured wind speeds will always take precedence. So just provide us the most accurate information you can. In terms of reporting wind speed, once you get upwards of light structural damage or shingles getting blown off or tree damage getting done, those are the types of things that we ask that you report, because those are significant. And if you have damage, you have trees down or power lines down or something of that nature, that's something that we need to know about. So please let us know about that if you can. If it's after the fact, you're welcome to let us know via the online system. But if you have something more time sensitive, we'd appreciate a call if you can. So this is a good screen to do a screen capture on, 757-899-2415. This is how you get a hold of us. For amateur radio purposes, you can get a hold of us on the amateur radio. Our net controllers will be able to take your report and relay them to us. If you follow us on social media, feel free to send us reports there. Email can be sent to akq-report@NWS.gov. And again, if you have cloud features or anything else, feel free to use that. And then, of course, the weather.gov/akq/report weather is your online reporting site if you're interested in reporting that. We are not going to cold call you. So we're not sure whether you're watching the weather or maybe you're not home. Maybe you're someplace else, and maybe you're not thinking about the weather at all. So warnings are going to take precedence. We're not going to bother you in those types of situations. So please help us to keep people safe. If you have something to report, please do report it. wx4akq.org is our site for all things amateur radio. So you can get net control and contact points and local training information, training resources. Our amateur radio folks do a great job, and they keep us apprised of what's going on. And if you have amateur radio, they're a good group to keep track of. On social media, feel free to report pictures to us, be it hail pictures, damage, snow pictures, whatever you've got, and be sure to identify yourself as a spotter. As far as spotter safety and wrapping up here on this on this class, we're looking at the weather safety for our spotters as being the utmost important. There is no magic bubble to protect you. Hopefully that's obvious. Maintaining situational awareness is key. Try to figure out which direction the storm is moving in, if you're a safe direction from it. Are there other storms in the area? Are you safe from lightning? These are the types of things that you should be thinking about. Do you have a way to get away from the storm? Because storms tend to change direction very quickly. So we want to make sure that you have a way to escape these storms if they were to move. In terms of lightning safety, there is a very quick lightning strike. Again, the tallest object in a field tends to be what gets struck by lightning. So we tell you not to be underneath trees or swinging metal sticks or hanging out in the water, all of which would be bad. But certainly you want to avoid high water, high ground, water, open spaces, tall objects, metal objects, canopies, things of that nature. Typically, if you're in a larger group, you're going to want to spread out, if at all possible, and ideally get indoors. If you are indoors, try not to use water or cords or anything like that. Stay away from the doors and the windows. If you can unplug and stay away from the appliances, that'd be great. Avoid power surges of any kind. If you happen to have plugged phones still at this point, those are things you might want to stay away from, because lightning can travel indoors through phone lines and pipes. Can be typically something that can cause issues that way. CocoRoss.org. If you do take rainfall measurements, this is a good way to get those reports housed online or hosted online. Report the same time every day, and those data points get sent to us. Really helpful for verification and research, and getting that information sent away to our media partners. So really, really helpful if you can do so. The MPing app, this is something you can pick up on Google Play or the App Store. Easily report anonymously about rain that you receive, or precipitation that goes over to snow, or damage from thunderstorms that you receive. Very quickly gets sent over to us. If you happen to have Radar Scope, back to Radar Scope, it does send that information through Radar Scope as well. So you'd be able to access that information through Radar Scope as well. Publications, this is our spotter field guide. You'd be able to get this information sent to us. It is linked on our spotter page. It'll also be sent as part of your spotter packet. So you will have that information available to you. Every part of this class comes out of this field guide. So you'll have all the information from this field guide to kind of refer back. Really, really good information. We used to hand it out automatically during classes, but we can't produce them anymore. So we just hand out the electronic copies. So really cool to download and put onto your smartphone or mobile device or your laptop, because it's chock full of information. There's really a lot of good stuff in there. If you are interested in a spotter certificate, just go to our webpage. There's a little drop down underneath the Get Your SKYWARN certificate. Click that Get Your SKYWARN certificate line. Put your first and last name in, put the class attended on here, and just get your certificate for that. If you are interested for your continuing education. This doesn't go anywhere. It's not logged, so you don't have to worry about your information getting saved or pushed anywhere because we're not seeing any of it. In terms of the spotter card, we no longer issue the spotter cards, but if you are interested, just go to that address. We'll have this linked on our webpage. Just put that spotter ID or that code in there, 2025 SKYWARN, uppercase S, everything else lowercase with no spaces. Just put your name. If you have a call sign or a spotter number you want to put in there, that's great. Otherwise, just leave it blank. Put your training date in there and then your code, and just hit create code. To follow the directions on there. If you have any problems, just let me know and I can help you. Otherwise, that's how you get your spotter cards now. Lastly, do's and don'ts. Please do brief yourself with the latest information. Please do understand the importance of your report. Keep yourself safe at all times, please. Express the uncertainties in detail in your report. Don't assume we know everything that's happening at all hours of the day or night. We don't. We're doing the best we can with the data that we have. Don't put yourself in harm's way for us or withhold a storm report because of uncertainty. And obviously, don't forget to pat yourself on the back for being part of this class today, for taking this class with us. We very much appreciate your help. We look forward to working with you. We very much love having our spotters helping us out as much as we possibly can. We thank you for being part of this class here today. I'll hang out for any questions y'all might have. Feel free to email us if you are watching this after the fact at akq-report@NWS.gov. But otherwise, thank you for participating in our class today. Have a great day, and hopefully you enjoyed this class.